And then this will be positive like whenever sine x is greater than half, right?
Yeah.
Cha-cha. Okay, so when is that true? Draw a picture for that. Sine's the y coordinate, so the y coordinate is bigger than a half, like from here to here, basically. So that's like pi over 6, and that's like 5 pi over 6, right? Okay, and then you kind of superimpose them into one, like, jumbo circle with overlapping shadings. Remember this? What? Yeah, I know. I always do the positive one by default because I think it's easier cognitively to work with, and then watch. Now we have to, so we have this figure, and what we have is a figure which is shaded when either of the two expressions, well, it's shaded, I shaded when this is positive, and I shaded when this is positive. Okay, so now, what is my actual goal? Let's make the thing first of all. So we're only going from 0 to 2 pi. So we go from 0 to 2 pi. This is f prime, and what am I doing? Oh yeah. So when does it change sign? It changes sign at
Pi over 6.
pi over 6.
Pi over 2.
Pi over 2. Something happens at pi over 2. Something happens at
5 pi over 6.
5 pi over 6. And
3 pi.
something happens at 3 pi over 2. Okay, so now we have to think for a minute. I want to know when this expression is positive, but since there's a negative here, that's really like the same thing as saying when like the product of these two is negative, right?
Yeah.
So I basically, in order to figure out when the derivative is positive, I need to see when one of these is shaded and one of them isn't. You following this? Okay, so the derivative will be positive when one of them is shaded and one of them isn't. So that's here from 0 to pi over 6. Here from 3 pi over 2, or sorry, from pi over 2 to 5 pi over 6. And here from 3 pi over 2 to 2 pi. So it must be negative here and here. Okay, so I know that my function is increasing here, here, and here, and decreasing here and here. All right, that was a more complicated example. But I think the general idea is the same. Okay. Last thing, basically, there's now a really important theorem. This is our last big important theorem for today. It is called the first derivative test. And the first, even though it's called the first derivative test, it's a theorem. And it is the theorem which enables us finally to conclude for sure that a function has a relative max or a relative min somewhere. Okay, so let's do it. Here's how it goes. Let C be a critical point. Let C be a critical point for some function f on the interval a, b. Okay, and here's what the theorem says. It says that if the derivative is negative on some interval AC, and the derivative is positive on some interval CB, then what can I conclude? Let's draw a picture. So here's A, here's B. At C, there's some kind of critical point. My derivative is negative on the interval AC, and my derivative is positive on the interval CB. What's happening at C?
The
Good question.
derivative is like 0.
Not necessarily, or does not exist, but that's not, but okay, but I already told you that's a critical point, so that's not telling you anything new. What does this theorem say? Look at it. Okay, it's a relative min. It's a relative min. Then f of c is a relative min, or f has a relative min at x equals c. F has a relative min at x equals c. Didn't I promise you, like last class or whatever, that we were going to finally be able to justify that a function had a relative min at a certain point? Well, here it is. Right. So let's prove it. Here comes the proof. Well, again, it's a conditional. So we do it. We go through all the things. Suppose that the derivative is negative on the interval AC, and that the derivative is positive on the interval CB. I need to show that f of c is a relative min. All right. What does it mean to be a relative min? What is the definition of relative min? Noah Fang, what's the definition of relative min? Yeah, he said that the points around it are bigger, right? Your relative min if you're the smallest in a neighborhood nearby. Yeah, so what we need to show, if we want to show that this is a relative min, we need to show there is an open interval. There is an open interval containing C. Such that f of x is greater than or equal to f of c in that interval. Everybody with me? Right. How am I going to do this? How can I prove that all the points nearby C are bigger than it? All right. Let's use what?
Well, it's like decreasing from AC.
Yeah, I know it's decreasing, and then
And it's increasing from AB.
that's pretty much it. Yeah, it's decreasing and then it's increasing. So let's actually just really just do it. This really just has two cases. Suppose x is so case one, suppose x is on the interval AC. If x is on the interval AC, then what do I know? What do I know? According to my assumptions.
F of x is less than
The derivative of x is negative. But if the derivative of x is negative, that tells me, based on my new theorem, yeah, f is decreasing on the interval. So here, I'll write a little x here. So here's x, right? So if x is on my interval, well, I know that my function is decreasing on the interval xc. Well, I guess it's decreasing ever on this interval AC. I guess I'll just write that. F is decreasing on the interval AC. So if f is decreasing on the interval AC, well, what is the definition of decreasing? The definition of decreasing is move to the right, go down. So since x is less than c, see the picture? I conclude, since my function is decreasing on this interval and x is on that interval, the definition of decreasing is move right, go down. Since x is less than c, f of x has to be greater than f of c. Right? Say right. Okay, and now case two is that x is on the interval CB. If x is on the interval CB, what do I know?
The derivative is greater than 0.
The derivative is greater than 0, which, based on my new theorem, tells me that f is increasing on the interval CB. Okay, so now I have a different x. X is over here somewhere now, and now I say, okay, since c is less than x, what is my which it is, what's my definition of increasing? Definition of increasing means move right, go up. So f of c has to be less than f of x. Okay? But in either case, I have shown that the points that are around f of c are bigger than it. Okay. That is the first derivative test. It's another thing that's kind of a little bit obvious. You're going to use the first derivative test probably 200 times this semester. It comes up again and again and again because proving that a function has a relative min at a particular place is one of the basic things that you do in calculus. Okay, so now we're just going to do one example, and then we'll be done for today.
Like a
Had an example somewhere. Yeah, here it is.
No, we don't have a calculus.
pretty.
Okay, so take this function f of x equals x plus 2 sine x on the interval 0 to 2 pi. Let's do this kind of fast. Take this function, find and justify all intervals where the function is increasing and decreasing. Find and justify all relative extrema. Okay, so double speed. Let's just take the derivative. 1 plus 2 cosine x. That was pretty easy. I need to figure out when that is positive and when it is negative. So I'll just do that now, right? When is 1 plus 2 cosine x positive? It's going to be positive whenever. You guys doing this? You're ahead of me or behind me?
It's greater than negative a half.
When cosine x is greater than negative a half. So draw a picture of all the places where the cosine is greater than negative a half. Cosine's the x coordinate, so it's gonna be big. It's like all this, right? Yeah. Okay, so I think I'm ready to make my number line analysis now. Here's 0, here's 2 pi. The sign changes at, in my imagination, you all shout out the correct answer simultaneously. As soon as I pause. 2 pi over 3, and then it changes again at 4 pi over 3. And looking at my picture, it's going to be positive here, then negative, then positive. Is everybody cool with this?
Yeah.
Okay, so from this I conclude that my function is increasing on the interval 0, 2 pi over 3, decreasing on the interval 2 pi over 3, 4 pi over 3, and increasing again on the interval 4 pi over 3, 2 pi. All right, now we get to the new stuff. The new stuff is justifying precisely where this function has a relative max and relative min. You tell me, does this function have, what's going on at 2 pi over 3?
0.
The derivative is 0, that is correct. But just the fact that the derivative is 0 alone does not tell me anything. Remember, right? The derivative can be 0 without there being a relative max or min. But what's actually going on in this particular problem at 2 pi over 3? Everybody do your hands with me. The derivative is positive. Then the derivative is negative. So what happened at 2 pi over 3? Relative max, exactly. There is a relative max at 2 pi over 3. Okay, there is a magic sentence which justifies this. And you should stick to this pretty closely. Here's what we say. We say f prime changes sign.
Good afternoon, Blazers. May I have your attention for one brief afternoon
To
announcement.
negative.
Varsity and JV Baseball, your study hall, is in room 242 after school today.
Can't get mad at her like I
Varsity
get mad
and
at
JV
us.
baseball,
So
your
nice.
study hall is in room 242 after
Oh
school
my God.
today. Have a great weekend, everyone.
Okay, F prime changes sign. F prime changes sign from positive to negative at x equals 2 pi over 3. So, by the first derivative test, F has a relative max at x equals 2 pi over 3. This is the magic sentence. It's not enough for the derivative to be 0. You have to mention that there is a change in the sign of the derivative. That justifies that there is a relative max. Do you guys get this? Okay, would someone please volunteer to tell me something else about this function? Does it have a relative minimum somewhere?
Yes.
Yes. Timothy, give me the magic sentence.
Prime changes sign from negative to positive at 4 pi over 3. So by the first derivative test, f has a minimum at x equals 4 pi over 3.
Yep. Perfect. Derivative is negative, then it's positive, so there must be a relative minimum. That's how the first derivative test works. Everyone get this? Okay, Brass will do like a little pan of the class. Everyone wave goodbye.
All right.
Do whatever you need to do in third period. Gang signs, middle finger, whatever you want. All right, turn it off. I think it's done.
Sure. All right. Just end it with